Welcome to Introduction to SSP, or System Structure and Parameterization to use its full name. So if we start with the executive summary of SSP, so if you forget everything, I will be grateful if you remember this. SSP is a tool-independent format for describing simulation of system structures. So it typically comprises a network of component models and their signal flows. Often that means a number of FMUs that are connected into a system. Compared to FMI, SSP adds the notion of parameter sets and metadata for documentation. Everything is packed up in a zipped file, although the system description is described with XML. And SSP is an open format in the sense that it's possible to add your own resources, data, metadata into the system structure. And that opens it up to be used for various purposes by different tools, from architecture to simulation. So let us look at the SSP format and architecture. If we start with the intended use cases, the focus has always been SSP as a simulation framework. So the SSP contains implemented components, real parameter settings. You import them into a tool to execute a simulation, although the solver settings are not defined by SSP itself. There are a couple of other uses as well. Becoming more and more popular is to use SSP as a lightweight format for designing system simulation architecture. So you can start by describing a system or a component design, its interfaces, parameters, connectors, and add documentation. And then other uses are to use them as templates for parameters or some sort of database for parameter sets. The structure of the SSP file, so it's a zip file. It has a number of folders, and inside there are typically FMUs, connection structure, parameters. Systems can have nested systems, and then there are other resources like data tables, metadata, documentation, etc. So in SSP, what is a system? So it has certain building blocks. So there are components and nested subsystems. There are connectors, sometimes called ports, and connections between ports. Then on top of that, you apply parameters. So you can declare system parameters, component parameters, hierarchical parameter sets, and there is a mechanism for name mapping from the data to your model. And in addition to that, there are additional resources like the FMUs, the documentation, metadata, etc., etc. So the relationship between the different entities are that you have a system structure definition, which contains one or more systems. The system in itself contains a number of elements, typically components, connectors, and parameter bindings. And also at the system level, you have connections between the different components. So the SSP says that every SSP file must contain one root system description that is always called systemstructure.ssd. The parameter bindings to systems or to components applies a set of parameter values to a component. And the binding can define either parameters that are either inline or with a reference to an external SSV file. So for an FMU, for example, you have the ability to set start values, parameters, and so on. And SSP, like FMI, supports the basic types and array constructs, but there is no record. SSV files can parameterize complete hierarchies of systems and subsystems by using a dot name convention. So SSV is an XML file, which is the default, but it's common that tools support other file formats, for example, CSV files. An option to the parameter binding is what is called a parameter mapping. So the parameter mapping gives you the ability to map names from the data to your model. So it breaks the dependency between the data and your specific model. And it also provides linear transformations of data as part of the parameter sets. Data can have unit definitions through the SI systems, but one problem is that SSP does not define an expression language. So you cannot describe, for example, that the volume is the base times the height. You can only apply linear transformations with constants. On the other hand, Daimler tries to get around that restriction by a creative abuse of the parameter set definition. So the typical workflows that SSP supports, you can start by defining your component architecture, the initial step of the design of a component. So you can define parameters, connectors, and documentation that provides an API with documentation. You can then apply that at the system architecture level. You define components or abstract component types. You define the connection topology and add documentation again. Then we can go into more concrete system simulation. That's where the components are populated with concrete implementation of the behavior. You apply the real parameter sets and very simple simulation setup. And then we can extend that further into what we call a credible simulation process, where you try to capture documentation about requirements, test scenarios, verification criteria, using a standardized metadata format. So the current developments are that we have, at the end of 2024, SSP 2.0 was released. The new features of SSP 2.0 is that it can also support Modelica components and connectors, so that there is a syntax for describing references to Modelica components as part of SSP. And there is also a new connector kind called undefined, which can be used to support ACALls and connectors in Modelica. SSP 2.0 has been extended with the basic features of FMI3, such as types such as float32, and array connectors and array parameters. Also, you can define local variables, for example. An important point to remember is that every file that is built according to SSP 1.0 is also compatible with SSP 2.0. So what happens now after 2.0? Well, we can expect a minor revision, SSP 2.0.1, with minor corrections in the specification, and can be expected any time now. And of course, we have started looking at what might be SSP 2.1, extending with terminals and icons from FMI3, maybe version management, maybe definition of time series data or bus connections. Well, all of this is work in progress, and it's mere speculation on my part. But I mean, it's a living project. Maybe we should also say a little bit what SSP is not. So first of all, SSP is not SysML. The focus has always been on simulation, not MBSE in the more general sense. SSP structure corresponds a little bit to the internal block diagram of SysML, but there are no requirements or actions, stakeholders. So there are all these other views in SysML that are not represented by SSP at all. However, there is still also seems to be a quite significant interest in SSP to be used as a lightweight tool-independent architecture description to carry through the entire development chain. One should also remember that SSP has almost no semantics. So it describes structure, but it inherits the semantics from what is connected up. So, for example, if you connect FMUs through an SSP, then you get the FMI semantics of your system. If you have Modelica components, you will get Modelica semantics of your system. And that is a deliberate choice, that there are no simulation semantics in SSP. And we should remember that SSP is not limited to plain vanilla type of system with connected FMUs. It can represent models with other languages such as Modelica, and it has the support for the parameter sets and variants based on parameter sets. So let us take a concrete look at a couple of SSP examples. So the first one is a very simple SSP. So I will demonstrate the required SSD framework in XML. There is one FMU component. It has a couple of parameters, but no connections at all. So the XML description starts with a preamble that describes the system specification, the description. There is a system with one element, the component. And let's continue with that in a while. And then there is some more setup at the end. So you can have a system geometry, a graphical geometry, and you can add annotations from your particular tool. So if we look at the component here, this is a common component type. It has a name. It says that it is an FMU. And it gives a source, which is one of the resources inside the SSP file. So it has a couple of connectors, real connectors, and they are of the kind parameters. So that's how you define parameters in FMI and also in SSP. And then there is a graphical component geometry as well. So the second example is simple but a little bit more challenging. It has two components and a connection between them. So this is a typical example of a ready-to-simulate SSP structure. So let's forget about the stimulus components initially. But we can see here that we have connectors, a component parameter here called J. Here I have, which is a real number with the unit. And then we have the connection between the components at the end here with start and stop connectors and also the geometry of the connection. So if we look at this a Modelica component here, so first we can see that the version has been bumped to 2.0, that is required. And it says that the component type is of type Modelica, and there is an additional argument which is the path to the Modelica component type. So the SSP file doesn't contain any Modelica code. It just contains references to Modelica. And we have a parameter type here. And because we want, in this case, we want to use the Modelica type, inherit the Modelica type, we describe it as a binary type of that is Modelica. And here in the parameter binding, which is in line here, we defined the value of a component here. We could add the unit definition if it was necessary also here at the end. So let us talk a little bit more about simulation credibility and what that means in the context of SSP. This is really an effort that is developed by the ProStep IFIP Smart System Engineering Group. So the idea is to look not only at the data representation, but the entire process for product development with simulation. So as part of the product development, the key point is that we are forced to make decisions based on simulation. So to be able to make a credible decision, we must have based that on a credible simulation process, which of course requires a credible modeling process. To support that, the group has developed something called SSP LS traceability, LS meaning layered standard. So it's designed to support traceability in the meaning of documenting the different steps and what should be performed and what has been performed to make a decision based on simulation. So the emphasis goes from modeling components and systems and simulation to the process of creating a credible result. So it's a standardized format, XML-based format, which is linked into the SSP framework because it's a layered standard. And it's designed to be very flexible and adaptable to all sorts of corporate standards for documentation and for setting up your processes. But it's split into different levels. For example, the decision task, the simulation task, the modeling task, and the simulation task. And for each of those, we have metadata. And those can then form the building blocks for building the credible decision process. So with metadata that is readable both for humans and also machine readable, adding documentation files to the SSP files, and through that supporting an incremental development process where the SSP file can be gradually updated with more information. And the SSP LS traceability standard was just released by Modelica Association. So, going back to the summary. So, SSP is a tool-independent format for describing simulation structures and system structures. It comprises of components and their connections, typically FMU components. Compared to FMI, it extends with parameter sets and metadata. Everything is packaged in a zip file. Descriptions are XML. And it's open in the sense that you can add your own resources, your own data, in order to support the entire process from architecture to simulation to decision making. Thank you very much.